Hi, I'm Travis and I'm an engineer on the academic team here at National Instruments. And today I want to show you a new way to teach a digital communication concept called quadrature phase shift keying, or QPSK for short. Using a hands-on approach, you can make these concepts exciting and relevant to your students. Quadrature phase shift keying, or QPSK, is an important digital modulation scheme because it inherits many qualities from the simpler phase shift keying modulation scheme while providing a higher data rate. QPSK is used in digital radios, like the ones used by police, Bluetooth devices, and also video broadcasting. As you may have experienced, students sometimes have a hard time transitioning to digital modulation schemes because of the disconnect between theory, various formulas, and the relation to practical applications. But communications courses don't have to be just math, homework, and simulation. With a software-defined radio, your students can experience a real-world signal in the lab to help them see the relationships between frequency, phase, and bandwidth. A software-defined radio is a device that connects to your computer to generate and acquire RF signals. When combined with the right courseware and programming environment, students gain a hands-on experience with real wireless signals. So let's get started. Here I have a USRP software-defined radio connected to my computer running a QPSK Lab example. Looking at the block diagram, we can see the source code for our QPSK Lab. This block generates random bits using the modulation toolkit which comes with LabVIEW Communications. The modulation toolkit gives your students easy access to commonly used communications functions such as generating a pseudo-random bit stream. Here, a Fibonacci PN sequence is generated. Next, we'll map the bits to symbols with a given QPSK symbol map. Every 2 bits will be mapped into one symbol. Next, a repeating 26-bit Barker code is added so the receiver can synchronize to create our frame header. This allows the receiver to easily identify the beginning of a packet. Then, the signal is upsampled so there are multiple samples per symbol. Doing this is what allows the pulse shaping filter to do its job in the digital domain. The modulation toolkit will generate coefficients for a root-raised cosine filter which will be convolved with the oversampled symbols. This is the pulse shaping step. An important and often overlooked step in the real world is to maximize the signal-to-noise ratio. One way to do this is to utilize the full scale of the digital to analog converter. So in software, we normalize the signal to plus and minus 1. Last, we'll continuously write this waveform to the software-defined radio, and the baseband signal is graphed along with its power spectra. Let's run the program and check out the graphs in the receiver. We can see in our graphs a time domain and frequency domain representation of our QPSK signal. Let's run the receiver. And it looks great. The equalized eye diagram and constellation graphs come through perfect since we have a cable connection. These are the exact steps students learn from their textbook and lecture, but rarely see in action. Now they have a chance to create a real-world QPSK signal. This is something you just can't do with a USB-based IQ receiver or spectrum analyzer. We were able to generate a QPSK transmitter from start to finish with the help of some modulation toolkit functions. We were able to view the baseband representation of the QPSK signal and also look at the occupied bandwidth by graphing a spectra. Communications doesn't have to be complicated. With hands-on hardware and courseware, students can make connections between theory and implementation. To explore this approach further, download the free courseware linked on this page.